This video is the first in a series about simple electronic devices. In particular, we'll start looking at resistors. A resistor is a component that limits the current in a circuit. We can see this by looking at Ohm's Law. The voltage V is the energy spent per electron in pushing a current through a device with resistance R. So for a given applied voltage, we can solve for the current. Here is a resistor. Let's place this in a simple circuit with a battery. Let's represent this circuit in a schematic drawing. This is the symbol for a battery or a constant voltage source. The battery has a positive end, represented by the longer lines, and a negative end, represented by the shorter lines. This is the symbol used to represent a resistor. It has some numerical resistance in units of ohms, we'll represent with R, and the battery provides an energy per electron measured in volts to drive current through the loop. By convention, the current moves from the positive side of the battery or power supply to the negative end. This is a convention that was set up by Benjamin Franklin, who guessed that the charge carriers in the wire were positively charged. We now know that electrons are negative charge carriers that actually are moving through the wire in the opposite direction to the current, but that's the convention that everyone uses. Current is said to move from the higher voltage to a lower voltage. Here are a few different size resistors. The value of their resistances can be read using an ohm meter. I'll start by switching the meter to the most sensitive range on the ohm scale. When the display shows only 1 as a single digit on the left, it indicates that the resistance is bigger than the maximum value for that range. Here we see that the full-scale value is 200. I need to continue turning the selector switch to the next higher range. As with most measurements, I'd like to read the value on the range that gives me the maximum number of significant figures, or the maximum precision. Here the full-scale range is 2 kiloohms, so I interpret this number as 0.459 kiloohms or 459 ohms. Here's a resistor that's physically bigger than our original resistor. Let's measure its value. Despite the fact that the resistor is physically bigger, we see that its resistance is smaller than the one before, so the physical size is not an indication of the electrical resistance. We can get an approximate value for the resistance of a given resistor from the colored rings that the manufacturer has painted on the device. Each color represents a digit, as given here in the table. Let's ignore the gold for a moment and start at the other end. I'll refer to these as A, B, and C. Taken together, the first two digits represent a number between 0 and 99. The third band gives us a power of 10, so it's a little bit like scientific notation. So let's try this out. The first band on the left is brown. That represents 1. Then we have black, which is a 0, followed by orange, which stands for 3. So we have the first two digits together are brown and black, or 10. Then we multiply by 10 raised to the third power. That gives us 10,000 ohms, or 10 kiloohms. Just to be sure, let's try another example. Pause the video and try this one on your own first. The first band is yellow, that's a 4. The next band is violet, that's a 7, followed by brown, which is 1. That translates to a 47 times 10 to the first power, or 470 ohms. Now let's talk about this fourth band. It represents the manufacturer's tolerance, or the error in the color code. Gold represents plus or minus 5%. Silver represents plus or minus 10%. Since we have a gold band, we have 470 ohms plus or minus 24 ohms. So the actual value should measure between 446 and 496 ohms. The physical size of a resistor is indicative of how much power it can withstand. Energy in volts applied across a resistor is lost as heat, so resistors can overheat and burn out. To avoid that, we choose resistors with higher power ratings when necessary. This little resistor is rated at 1/8 of a watt. The bigger one is 1/4 of a watt. Then we have a 1/2 a watt, a full watt, and finally 5 watts. The power that is consumed is the product of the current and the voltage applied to a device. In calculating the power, it is sometimes convenient to use Ohm's law to substitute for the voltage and express this in terms of current only. Alternatively, we can write this in terms of voltage by substituting for I in terms of V over R. If we have two or more resistors in succession in a loop of the circuit, we say they are in series with respect to each other. We diagram that situation this way. The same current travels through the first and then the other. The result is that the two resistors in series provide a net resistance equal to the sum. If, on the other hand, the two resistors are placed in the circuit in such a way that they provide parallel paths for the current to travel, the front leads of the two resistors are in contact with each other and the trailing leads are in contact with each other, the resistors are said to be in parallel with each other. This combination leads to a lower net resistance since we've provided more than one pathway for the current to travel. In this case, the reciprocal of the net resistance is equal to the sum of the reciprocals of the individual resistors. With a little bit of algebra, we can show that the net resistance is equal to the product of the two resistances divided by their sum. Let's illustrate these two rules with a simple calculation. Let's imagine we have these two resistors in parallel with each other, followed by a third resistor. Let the two in parallel be 10 kiloohms and 20 kiloohms, and the third resistor 30 kiloohms. So we want to calculate the net resistance. First, we'll obtain the resistance for the two parallel resistors, which is the product of 10 kiloohms times 20 kiloohms divided by their sum, 10 plus 20. So that's equal to 200 over 30, or 6.6 kiloohms. So the net resistance is going to be this parallel resistance value in series with the 30 kiloohm resistance, or essentially 36.6 kiloohms.